inviting me to speak here. So I want to speak, I'm going to talk about something that's sort of different theme from, I guess, as it turned out, the rest of the speakers, but well, it's definitely about boundaries, and it's definitely about groups. And well, this is like a subject that it would be nice to have a more hyperbolically minded geometric group theorists sort of think about. So I'm going to talk about. So so basic overview. So given a random walk in a group, we're going to consider and associate topological boundary, which is called the ratio limit boundary. And its definition, I mean, its definition is sort of a very intuitive thing, but it was the reason it's defined this way is motivated by C-star algebras. So it turns out this boundary describes a certain C-star algebra, which called the Toeplitz algebra, which lots of people are interested in. So I won't talk that much about C-star algebras today, but well, I'll almost not talk at all. But well, as I will specify, like some of the problems I will mention are motivated by C-star algebras. So okay, you have this topological compactification. So it's a topological compactification associated to a random walk. You know, the Poisson boundary was a, well, it was a measure. It wasn't the topological boundary. This will be a topological boundary. And yeah, so we want to relate it to some geometric compactifications of the group. So yeah, and we'll talk about some problems about this compactification. So okay, so the overview is so we're going to have a finitely generated infinite group. We're going to have a probability measure on this group gamma, which I also sometimes call G, unfortunately. And the support generated by mu is going to, like, the semi-group, well, generated by this support is assumed to be everything. And as already has been discussed in Julia's talk, so you have a Markov chain and this group called the mu random walk. So the probability going to G to H is the weight that your measure assigns to G inverse H. And, you know, this is an infinite group. So as you take more and more steps, you can go to sort of more and more places. So for each X and Y, the probability that if you start at X, at n steps you'll be in Y, you know, which is, well, the n-fold convolution of X inverse Y, you expect this to decay to 0. So the question is, what can you say about these rates of decay? And this is sort of, and these rates of decay actually, you know, tell you a lot about this random walk, well, about this group. So we say that the mu random walk satisfies the ratio limit theorem if these probabilities Pn of xy divided by, so normalized by Pn of E is the identity, comma y, converge to something. So if these converge to some function h. So suppose, yeah, so suppose now this random walk satisfies ratio limit theorem. We'll talk about, so some, well, very natural examples where this is the case. Although in a lot of natural examples, this is still not known. So, but let's talk about this later. But so suppose this random walk satisfies a ratio limit theorem. So using these kernels, h of xy, you can embed G, the group, into the space of all functions from G to R, which vanish, well, this is not vanish, which, but equal 1 at the identity. So using this embedding. So this, so okay, G is countable. So, this space of function has a topology, which is given by, well, pointwise convergence. And the closure of the image of G in this function space is called the ratio limit compactification. And the complement of G in this space is called the ratio limit boundary. And we denote it this way by partial R of G mu. R stands for the ratio. And this should be reminiscent of the way you construct Hora function boundaries. Like, I think, you sort of, again, have these Boozman functions that Kazira talked about yesterday, for example, and you use these Boozman functions to embed the group into the space of all functions in the group, and then you take the closure there. Yeah, so any questions? Okay.
Ilya, when you say when you say the closure of the image, does it matter which topology you choose? Because like with Boozman, some people choose Lipschitz convergence, like Lipschitz norm, or the.
I mean, so this group is so this is uniform convergence and compact. Yeah, I mean.
All right, thank you.
Yes, of course, you need to choose a topology on the space of functions, and this topology is uniform convergence on compact sets. But since G is countable, so it's discrete, so uniform convergence on compact sets is and any other reasonable mode of convergence is like pointwise convergence. So a sequence of functions from G to R converges to another function if they converge pointwise, like at every point of G. Yeah.
Right, thank you. Yeah.
Actually, can I ask you a question?
Okay.
So is this function unbounded or is it or not? I can't tell completely.
This in general, this will be, I mean, it might be
exponentially decays, it feels, so it should be maybe bounded, but I'm not sure.
No, wait, the ratio, I mean, the ratio will not necessarily, it will not necessarily be bounded. Yeah.
Not necessarily bounded, or like even in the hyperbolic groups or something, it will not be bounded. Like in a free group, this is
Right.
not bounded.
Yeah.
Why not?
Because
it go down like exponentially.
Well, no. The exponentially. So what goes down in hyperbolic settings, what goes down exponentially is this thing in n. Like if you take Pn of xy,
right?
This goes down exponentially in n.
No, but as x, like as g goes to infinity, the function h dot g.
I mean, it depends on. I mean, it depends. Okay, for example, you could choose x here, or you could choose x here.
Yeah. No, but just put e instead of g, then you get a function. Is that a bounded function or is that an unbounded function? That's my question.
Put e instead of g, you will always get 1.
No, you could get a function.
X e. So you're asking Pn of like x e over Pn of y comma e.
No, e comma e or something. Yeah. Okay. No, y comma. Yeah. Is that right?
I mean, yeah. I mean, then of course it's going to be unbounded because you can choose x and y to be anything. I mean,
right. As x goes to infinity, this is a bounded function, right? Yeah.
As x goes, yes, that's right. Yes.
Okay. Thanks.
Yeah. So just some mumbo jumbo about C-star algebras. Who cares about ratio limit boundary? So you can define a certain C-star algebra associated with this random walk, in fact, with any stochastic matrix. So it's a C-star algebra of some operators on all functions on this group. And so this is something that C-star algebraists care about for their silly reasons. But one Adam Doron, who is my neighbor in Haifa at the neighboring university, like up the mountain, showed that this can be expressed in terms of the ratio limit boundary. And so there's a question of interest of C-star algebraists, whether this Toeplitz C-star algebra always has a unique minimal non-trivial G equivariant quotient. And it turns out that this would be implied using this complicated formula that Adam Doron came up with the C-star algebra in terms of this ratio limit boundary. This is implied by the action of the group on the ratio limit boundary being minimal. So this led to a question that, suppose this group with this measure satisfies a ratio limit boundary, and this shouldn't be there, and the ratio limit theorem and the ratio limit boundary is infinite. So is this action necessarily minimal? So the answer is we think not, but we couldn't come up with counterexample, and so this led thinking about like other kind of probabilistic compactifications that we're familiar about, like Martin boundaries. And okay, so this is what motivated sort of me thinking about this. Okay, so what's known about ratio limit boundary? So I'll say in a moment so for example, when G is amenable and mu is symmetric and finitely supported, this function is equal to this kernel h of xy that I defined in the first slide is always equal to 1, which means this compactification is a single point. So that's not too interesting. When the group is hyperbolic and mu is symmetric and finitely supported, Wolfgang Woese showed that this ratio limit boundary is equivariantly homeomorphic to the Gromov boundary of G. So this is very nice. It doesn't depend, it doesn't depend on the random walk as long as it's symmetric and finitely generated. Well, it doesn't actually even have to be finitely generated. Super exponential moment is enough. But anyway, so it's homeomorphic to the Gromov boundary of G. So in this case, the action is certainly minimal. So when you do something, we can do something for hyperbolic groups. You want to generalize to relatively hyperbolic groups. And when G is relatively hyperbolic and mu is symmetric and finitely generated, myself and Adam Doron showed that the conical points of the Bowditch boundary equivariantly embed into this compactification. So this is all but, this is all but.
Can you, maybe I just forgot the definition. So this compactification is just the image and the image in this like functional space. You just take the compactification there and you remove the interior, right? Is that what you do?
Yeah. You take the compactification and then you remove and then you remove the actual functions you get by actually like embedding the group elements. Yeah. So you take the
For the hyperbolic case, don't you have to quotient these functions by like functions that differ in finite sets or something, or like you?
So you do have to. Well, you do have to quotient out, but it doesn't. So it doesn't change the boundary.
Okay, thanks.
Yeah.
I mean, in the Horror functions compactification case, it's not true that if you do the same thing with the Horror functions compactification case, you don't get a homeomorphism to just the compactification minus the image. You have to quotient by functions that differ on a uniform set, right? But here you're saying you don't have to here.
Wait, what do you mean functions that differ in a uniform set?
Like if you do if you do the exact same embedding as you did before, but you do the Horror functions, you do just you embed them in the space of amusement functions.
Yeah.
Then the compactification minus the image is not the Gromov boundary. It's a little bit larger. You have
it's not. Yes, absolutely. Yes. In this case, this is the Gromov boundary on the nose. Yes.
Yeah. Okay. Got it. Thanks. Yeah. Cool.
Yes. Yeah. This is So I will explain. So this is not entirely surprising. So I mean, but yeah. Right. Right. So for relatively hyperbolic groups, myself and Adam Daron showed that the conical points of the Borish boundary covariantly embed into this into this ratio limit boundary. So the conical points are sort of limit points of geodesics in the Cayley graph, which don't get sort of permanently stuck in a uniform neighborhood of a coset of a parabolic subgroup. And so in progress, we're showing, so we're close to done, I hope. So that in general, so if you have a G which is hyperbolic relative to virtually abelian subgroups, so this is a class which includes a Kleinian group, or geometrically finite Kleinian groups, for example, then this ratio limit boundary is homeomorphic to something called the Martin boundary at the spectral radius. So I'll define it later, but by work of so myself and Dussol, building on the work of myself, Dussol, Gerasimov, Patihaylo, and Gerasimov, Patihaylo, Yang. This is obtained by taking the Borish boundary and then blowing up some of the parabolic subgroups to sphere of dimensions of one less than the dimension of the stabilizer. So it might not be all of, so I will explain soon which parabolic subgroups you actually have to blow up. It's sometimes all of them, sometimes none of them. So this is kind of a subtle question. But in this case, the action on the boundary would also be minimal. So yeah. So actually, we're hoping that there might be some example, some relatively hyperbolic example, when the action will not be minimal. But we can't get there yet. So right. So how would one, try to prove ratio limit theorem? So usually you do it by proving a local limit theorem. So what does it mean, a local limit theorem? So a local limit theorem means you want to sort of prove exact multiplicative asymptotics of the decays of this transition probabilities of if you start at X, what's the probability of being at Y after n steps? And this is multiplicative asymptotics, of course, as n goes to infinity. So when G is hyperbolic, Gazelle proved, this is 2012, proved that these things decay like this. So there's some C of xy, some function that depends on x and y, times the spectral radius of the random walk, which, so this thing is always less than 1 for an unamenable group, times n to the minus 3/2. And when G is relatively hyperbolic, under some assumption, Dussol proved the same asymptotics. when these assumptions failed, instead of, well, I'll say a bit later, instead of n-3 halves, you have a different sort of like n to something else. But in any case, whenever you have a local limit theorem, you can, quotient this out. So, and you would also have, so you'd quotient this out, and you'd be left with this. So if you have a local limit theorem, you also have a ratio limit theorem. So in both cases, the proof of the local limit theorem uses a careful analysis of the so-called Green's function, the spectral radius, and identification of the Martin boundary. So these are terms which I will explain now, but I'll start with the question. So first, hard question. Can you prove local limit theorems for other groups that have been discussed in this week? For example, mapping class groups and groups acting geometrically on rank 1 ket 0 spaces. So this is a good problem, but it's really hard. So a different problem which no one has really thought about, not no one, but like 5 people, and maybe we're not like the smart cookies in the jar, the smartest cookies in the jar. So like, can you prove a ratio limit theorem without proving a local limit theorem? So I think this would be very interesting, like, first, because so maybe a more elementary way of proving of a local limit or proving a ratio limit theorem without determining these exact asymptotics. Maybe for these groups, maybe for any non-amenable group of your choice. Okay, so what is the Green's function? So you still have random walk. So you have a measure and a group. So you define GR of XY to be this weighted sum. So you look at the probability of going in n steps from x to y, and you weight it by r to the n. So this either converges or diverges for all x comma y, for all x and y. So either it converges for all of them or diverges for all of them. And since G is non-amenable, the radius of convergence of this series is greater than 1. And so it's greater than 1. And this series actually diverges. Oh, sorry, it actually converges at its radius of convergence. So there's some maximal number like capital R, which you can scale this by, such that this series still converges. So I should mention, so if R is equal to 1, this has a nice sort of probabilistic interpretation. You can think of it as the probability that like a path sort of a mu trajectory starting at x ever reaches y. So when R is greater than 1, this sort of probabilistic interpretation doesn't quite work, but it's still a useful way to think about things. So you have this thing. So this is the weighted Green's function. So the Green function weighted by R. And so if you take minus log of this thing, you get an asymmetric metric on G, which is called the Green metric. And so the Martin boundary of this thing is defined to be the Hora function boundary of this green metric. So this is sometimes called the R Martin boundary. Okay, so what does it mean to be the Hora function boundary of the green metric? It means you can sort of get it in a similar way as you got the ratio limit boundary on the second slide. So let KRXY be this thing. So GRXY divided by GR of EY. So this is called the, something's called the Martin kernel. And again, you can get an embedding into the space of functions on R, which, well, instead of vanish, but say equal to 1 at E using this embedding. And, the closure is called the Martin compactification. And the complement of G in this compactification is called the R Martin boundary. We denote it this way. Okay, so this is the Martin boundary is actually, so unlike the ratio limit boundary, it's been studied for at least 80 years. I mean, Martin defined it in slightly different setting in like 1939. So, so we want to see how the Martin boundary relates to the ratio limit boundary. And okay, so if you're a mediocre calculus student and I ask you this question, you would probably say that they are the exact same thing, because okay, what's KXY? It's the sum overall and so Pn xy r to the n divided by the sum of Pn of xy, Pn of ey r to the n, and this is the same thing as if you only take like the last term. Right? Because, okay, of course, you're a mediocre calculus student, so the other terms shouldn't matter. So this cancels out and you get h of xy. So there are sort of very naive reasons to believe that these would be the same things and that they wouldn't depend on RR, but this is not the case. So there are finitely supported measures on amenable groups, for example, lamplighter groups, for which the R Martin boundary is, well, infinite for any R, but the ratio limit boundaries, actually for amenable groups, R is equal to 1 here, but nevertheless. But the ratio limit boundary of symmetric random walks in amenable groups, like I mentioned before, is always a point. By the way, that's the theorem of Vez. So conjecture that's sort of, well, Adam and I feel kind of bold about is that the R, so if R is 1 over the spectral radius, so it's the maximal thing that you can scale by, the R Martin boundary actually always equivariantly covers the ratio limit boundary. So the connection, so one of the reasons we would think this is true is that points of the Martin boundary, of the R-Martin boundary, and the ratio limit boundary are both something called R-harmonic. So we talked about harmonic functions, harmonic functions in like all of Julia's talks, and harmonic functions are the functions that are one harmonic. So what does this mean? It means if you have an unbounded sequence like yn, and you suppose that these functions converge pointwise to like some function, which will then be by definition in the, well, respectively, if you take this in the Martin, let's say R, so in the Martin compactification, or the ratio limit compactification, then if you average this function over your random walk, you'll get this thing back. So if it was one harmonic, you'd get f on the nose. Instead, you get this. So another way to say this is that these harmonic functions, these functions will be harmonic for the measure r times mu. So yeah, harmonic for the measure r times mu. Okay. So, right. So, any questions on this? Okay. So, I want to mention. So, what's the R-Martin boundary of relatively hyperbolic groups? So let G be relatively hyperbolic. R is at most, well, anything up to the spectral radius, and mu is finitely supported. Then the R-Martin boundary, so for any R, the R-Martin boundary of this random walk will cover the Bowditch boundary of the group. So this is a theorem of myself, Gerasimov, Patihailo, Yang. If R is equal to 1, and myself and Dussel for general R. So this is the hard part actually like happens when R is equal to R. So you need a more complicated argument there.
What do you mean by cover?
Sorry?
What do you mean by covers?
Yeah, so it means the identity map from G to G extends to an equivariant map from the Martin boundary into the Bowditch boundary, or well, from the Martin compactification to the Bowditch compactification, and then you can restrict it to a homeomorphism from the Martin boundary to the Bowditch boundary. Sorry, not the identity map from G to G extends to equivariant surjection. So from Martin compactification to Bowditch compactification. Right, so this is it's equivariant surjection. And you restrict it, if you restrict it, so this restricts to an equivariant surjection from the Martin boundary to the Bowditch boundary. Yeah, that's what I mean.
What was the case in the previous boundary? I forgot, like the one defined in the second slide. I forgot what you called it, the HX.
In the ratio, right? So in the ratio limit boundary, we're not quite sure yet that this is the case. I mean, this would,
yeah.
So we have partial result. Yeah. So I mean, so we expect, yeah. So the conjecture is that it will, yeah. So the conjecture is that it will always cover, always, yeah, that the Martin boundary will always equivariantly cover this ratio limit boundary. For relatively hyperbolic groups, I mean, we think that you would have the same map, but we can't prove it yet. Yeah.
Okay. Yeah. Thank you.
For relatively. Okay. So this is also, yeah. So for the Martin boundary, so the preimage of any conical point in the Bordage boundary, in the Martin boundary, is a singleton. So what discussing what happens, so the preimages of parabolic points are more complicated, even for groups which are hyperbolic to virtually abelian subgroups. So if R is less than the spectral radius, then for a parabolic point in the Bordage boundary, whose preimage is virtually ZD, the preimage is homeomorphic to the sphere of dimension d-1. So actually, if this is a non-uniform lattice in H3, then the Bordage boundary will be this Sierpinski carpet, so a sphere with an equivariant family of disks removed that Kim talked about in her talk. So if you add the spectral radius, then the preimage may be either SD-1 or a point, depending on whether the random walk is something called spectrally degenerate with respect to the parabolic subgroup. So what does it mean to be spectrally degenerate? So let P be a parabolic subgroup, and let mu P be the induced submarkov chain on P. So if you take an element of P, let mu P of G be the probability that a sample path of the mu random walk, that it ever returns to P, and that it first does so at P. And so this is not really a probability measure. This is a measure of total weight strictly less than 1, because P is like a transient subgroup, so there's a positive probability that if you started the identity, you just never go to P. So the spectral radius, okay, so we want to look at the spectral radius of this induced random walk on mu P. So because sort of in the Green's functions of mu P, you're sort of summing over fewer elements. So, it should be easier for a scaled series there to be finite. So this means that the spectral radius, it means that R mu P is greater than or equal to just R of mu, which means the spectral radius of mu P is at most the spectral radius of mu. The measure mu is said to be spectrally degenerate with respect to P if these things are actually equal. And so this is sort of a bad situation. So this means that the random walk assigns that this measure mu assigns too much weight to P. And actually, this never happens if P is virtually ZD, if D is less than or equal to 4. So for a general relatively hyperbolic group, we expect the preimage of a parabolic subgroup P in the Martin boundary to be the Martin boundary of this induced measure on the parabolic subgroup. So what is this Martin boundary of induced measure in the parabolic subgroup? Dussol finding, well, in slightly different level of generality. So Dussol recently, generalizing work of Nate Spitzer from 1960, showed that if you have sort of sub probability measure on Z to the D, or a finite extension of that Z to the D, then the Martin boundary is homeomorphic to the sphere of radius of dimension d-1. So this is sort of different situation than if you take actual symmetric. So if you take a symmetric probability measure on Z to the D, then the Martin boundary will be a point. Otherwise, so if it's not probability measure, but like total weight less than 1, then the Martin boundary will be a sphere. So the proof of local limit theorems and ratio limit theorems uses the identification of the R Martin boundary of G mu, and it uses specifically a tool used in the identification of the R Martin boundary. So R is specifically at the spectral radius called the Ancona inequalities. So this is sort of useful technical trick that says that random walk sort of behaves well with respect to geodesics, which I will talk about. So now, are there any questions? Okay. Yeah. So this is, I want to skip, these are like.
Ilya, I have a question.
Yeah.
I didn't understand. Do you have a map from ratio boundary to the Bowditch boundary?
No, I mean, not yet. Yeah, no, we don't.
So you have only injection on the conical point to the Martin boundary, right?
That's right. Yeah, we have
conical point in Bowditch boundary.
Yes.
Pre-images
Yes.
are just points, right?
Yes. Yeah. Yeah. So we have a map. Yeah. So this identity map extends to a map from to a one-to-one map from the conical point in the Bowditch boundary into the ratio limit boundary. Yeah. But we do not know whether there is a map from the ratio limit boundary or like.
Even when parabolic subgroup are virtually abelian.
Yes. Yeah. That's right. Yeah.
You don't know even in this case.
Yeah. I mean, I think it's true. No, wait. Well, yeah, no. If parabolic subgroups were virtually abelian, we're actually. We think we do know that this coincides. That this is the same
As a Martin
as
boundary.
the Martin boundary at the spectral radius. Yeah. Yeah,
see.
but the proof is somehow it's different and doesn't. Yeah.
I see. Okay, thank you.
Yeah. Right. So I want to talk about these sort of Ancona inequalities. This I want to skip. Yeah. So these important tool for proving these definition, these local limit theorems, there are certain inequalities. So in a hyperbolic group, if you have some points x, y, and z in that order along a word geodesic, so a random path from x to z. So Ancona proved that the like sort of a random path from x to z has a uniform probability of passing through y. So this means if g, you take the unweighted Green's function, then g of xz is less than or equal to c times g of xy times g of yz for a uniform constant c. And so, this probability could be interpreted as like g of xy. So the probability of that the path from x to z passes through y is like g of xy times g of yz divided by g of xz, and this would be greater than c inverse. So it turns out the same is true for GR for R less than or equal to R. So for R less than so this is so for R equals to R, this is a theorem of Guzel. And you can interpret it by taking the minus log of everything, that this green metric d mu equals minus log g is roughly additive along word geodesics. So it means for all xy in this group, which for some reason I'm called gamma again, d mu of, so you have x, y, and z points along this geodesic, d mu of xz is greater than or equal to d mu of xy plus d mu of yz minus d. In particular, this would mean
maybe well, finish your sentence. Sorry.
In particular, this you can show that this would imply that mu is hyperbolic. Yeah. So
I want to exactly actually ask that. I was going to ask if this characterizes hyperbolicity, and it seems like
that what that it's the characterized hyperbolicity for the green metric.
If you have like a group where you have this inequality for any geodesic.
Yes, I think I actually thought about this with Leonid like I think 3 years ago, and we couldn't and we couldn't figure this out. Like we thought about this, I think, in Leonid's office.
And Victor.
Yes, and Victor, yes, of course, yeah, and Victor, yeah. Yeah.
So yeah, I mean, just sort of in the spirit of this conference, does something like this work for like Morse geodesic? Like if you take them along a Morse geodesic or something, like if you're not hyperbolic, let's say, or
yeah.
Okay.
If along with that, so you're saying if you take the point, so for an arbitrary group, you take some points along a Morse geodesic. This is true. Yeah.
Okay, cool. Yeah.
This is along a Morse geodesics. I mean, this is well, it's only a theorem in hierarchically hyperbolic groups and relative. So and so this is so myself, so Cordes, Dussol, myself. And we actually use this to show that, so yes, I should have mentioned this, that we use this to show that the Morse boundary in hierarchically hyperbolic groups embeds into the Martin boundary. And the argument works for any Martin boundary R less than equal to R or R equals to R. So this is a conjecture. Okay, this is like, so question, which is interesting. Does the Morse boundary in this setting of relatively hyperbolic groups, sorry, in the hierarchically hyperbolic groups, always embed into the ratio limit boundary? And another interesting question in this context is whether the main sort of guest of this conference, the sublinearly Morse boundary or sublinearly contracting, whether this embeds into the Martin boundary. So these are all sort of yes, these are sort of interesting questions. So along sublinearly Morse geodesics, so along Morse geodesics, you can have this sort of inequality on the nose. Along sublinearly Morse geodesics, you do not have this inequality on the nose, but maybe you have something else. Like naively, maybe you'd expect this D to grow like sublinearly along the geodesic. Okay, but I don't, but like I tried to think about this and somehow it didn't, well, it wasn't easy and then I gave up. But I think it's a reasonable, this is like a very interesting, I think I thought about this with Yulan, and we talked about, I talked about this to many of you, and so this kind of inequality, so in a relatively hyperbolic group, so you can ask similar sort of, so there are these similar inequalities, so like Konkonai inequalities. So if a group is relatively hyperbolic, then it acts geometrically finitely on a proper geodesic Gromov hyperbolic space. So the Bowditch boundary is the Gromov boundary of this space. So you should think of like non-uniform lattice in H3, acting in H3. And you have similar type of Konai inequalities here. So well, except now you have to look at geodesics not in the Cayley graph, but in X. So suppose you have 3 points sort of in the group G, H, and W, and the geodesic in X from G to W is within D of like this orbit point of H. Then this sort of inequality holds along that geodesic. So this also works. So this is myself and these gentlemen prove that this works for the unweighted Green's function. And so with Dussol and myself, we proved that this also works for the Green's function weighted at the spectral radius. So this is a more complicated proof, but I want to state conjecture now. Conjecture. So prove the exact same sort of inequality for the mapping class group acting on Teichmuller space. So that if you have a point, so instead of this, so instead of X, you have this Teichmuller space, the mapping class group is sort of a non-uniform lattice in Teichmuller space. So prove that if HO, so O is a base point to Teichmuller space, and HO stays close to the Teichmuller geodesic from GO to WO, then you have this inequality. This would be very useful. This would open the door for local limit theorems and the mapping class group, and all sorts of other things. So this is, something. Well, yeah, I think this is something. Yeah.
Just so I understand. So you're saying you don't think this would be true for any geodesic, any Teichmuller geodesic, but you take something.
I think this.
Parts or
I wouldn't be this. I wouldn't be surprised if it would be true for any Teichmuller geodesic, because the fact that HO is close to this geodesic implies that this point is that the nearest point here is in the thick part. And when Teichmuller geodesics are in the thick part, they in the thick part they sort of look kind of like hyperbolic geodesics. So this I think might be true for any Teichmuller geodesic.
I see. I think I missed the quantifiers. So these quantifiers basically do say that you have to be in the thick part, and then. Yeah.
Of course you have to be. Yeah, of course you have to be in the thick part, because if you're in the thin part, there are no orbit points nearby.
Thank you.
Your thick part is like the D neighborhood of this point O in moduli space. So maybe since I have some time, I want to talk about a useful thing that we used in with Leonid and this other gentleman to identify this map, to have this map from the Martin to the Bowditch boundary, which is the Floyd metric. And this is somehow, well, so far has been difficult to generalize to groups that are not relatively hyperbolic. But this is kind of somehow a tool which reduces this study of this kind of random walks and groups with hyperbolic properties, reformulates it in a way that doesn't use any hyperbolic geometry. It uses sort of this kind of combinatorics. So suppose you have a continuous integrable function on the positive reals, which decay at most exponentially. So it suffices, to consider r to the minus 3. And suppose you have a finitely generated group with a word metric. So for a finitely generated group, okay, gamma and base point in in this case in gamma. So you could rescale the Cayley graph so that the length of an edge becomes f of this distance. So the induced, so you should think, edges which are far from the base point are short. So this induces like path metric on gamma, because each edge now has a number assigned to it. So this path metric is bounded on gamma. Its completion is called the Floyd compactification. The remainder of this completion is called Floyd boundary. So amenable groups have Floyd boundaries that are either 1 point, or in the lonely case of Z, 2 points. That's kind of a unique case. It is not known whether there are groups which are not relatively hyperbolic with infinite Floyd boundary, but all sort of generalizations of relatively hyperbolic groups that have been considered like relative, mapping class groups, or out of N, or groups acting on, or like right angle, like graph products, like right-angled Artin and Coxeter groups have Floyd boundary, which are a single point. In fact, a sufficient condition for the Floyd boundary to be a single point is that like you could reach that, like if you have 2 points G and H in the group, then you can reach go from one to another by intersecting by like copies of Z2 which have infinite intersection. So of course in the mapping class group you could take like mapping class groups of subsurfaces.
Ilya, you didn't you didn't mention Victor's theorem that relatively hyperbolic group have an infinite Floyd boundary.
It's in the next. It's
sorry. Yes, sir.
So yeah, so Gerasimov theorem. So okay, so that's the picture for like non-relatively hyperbolic groups which are not relatively hyperbolic. If you are relatively hyperbolic, and so f doesn't need to be sub-exponential here. So, but you always have a map for the map from the Floyd boundary to the Bowditch boundary. So that's the theorem of Victor Gerasimov. And well, the preimage of conical points are singletons, and the theorem, I think this part is by Gerasimov and Patihailo. Gerasimov by these two people, that the preimage of a parabolic fixed point in the Bowditch boundary is homeomorphic to the Floyd boundary of the stabilizer subgroup. So if your stabilizer subgroups are like something reasonable, like virtually abelian, then this preimage will be a point. And sort of a corollary of this, it basically comes out of Gerasimov's theorem, that there's sort of characterization of what, so I think this is stated in our paper, but it's really, okay, in Gerasimov's theorem. So that if you have, like, what does it mean to have a Floyd boundary, Floyd distance, like bigger than something? So you have a group acting geometrically finitely on the space, and you have this, again, this picture, GH, so WX and HX. So the Floyd distance is bigger than like something if the distance between this geodesic from G to W in X and HX is less than something. So this is something like a visual metric for hyperbolic groups. Okay, so this means this kind of Ancona inequality that was proved by myself, Gerasimov, Patihailo, Yang, for the unweighted function, and then myself and Dusolov for the weighted function, could be reformulated as follows. So let G be a finitely generated group and mu a measure and gamma, so say it's finitely supported, a super exponential moment is good enough, then there's a increasing function on the positive and the reals, such that you have this inequality depending on the Floyd distance. And so this actually has as a corollary, you get this inequality here in terms of the space, in terms of geodesics and the space in which the groups act geometrically finitely. Okay, so the last thing I want to do is that this is kind of I don't know, a very elegant argument that this inequality for the Green's metric, for the this kind of inequality in terms of the Floyd metric implies that there's a continuous rejection from the Martin to the Floyd boundary. So I'm going to have a very short argument that this map, that this inequality sort of easily implies this map, the existence of this map. First I want to say that combining this Martin to Floyd map with Gerasimov's Floyd to Bowditch map, we obtained the desired map from the Martin boundary to the Bowditch boundary. So let's go from this Anconi's inequality to the map from the Martin to the Floyd boundary. So suppose toward a contradiction that you have a sequence of points xn and yn that converge to the same point in the Bowditch boundary, the same point in the Martin boundary by different points in the Floyd boundary. This is what you want to rule out. Okay, so this means there exists a single number delta such that for large n, we have the Floyd distance between xn and yn bigger than delta, because this is the beauty of the Floyd metric is that it's actually a metric on the whole compactification, and it sort of treats points in the group and in the boundary on equal footing. So, okay, consider a point x and gamma. By the triangle inequality, for each large n, we have either this distance greater delta over 2, or this greater than delta over 2. So in the first case, the inequality on the last page implies that g of x comma xn divided by g of o comma xn is less than c times g of x comma o by this inequality on the nose. And similarly, in the second case, you have the same thing with yn in place of xn. So now you take n goes to infinity and use the fact that xn and yn converge to the same point alpha in the Martin boundary. And this means that k alpha of x is going to be less than c times g of xo. Okay, so why is this impossible? The right-hand side goes to 0 for all x and gamma. The left-hand side is a harmonic function. So if you're using the unweighted green metric, green function, it's a harmonic. If you're using the weighted Green's function, it's a Green's metric, like gr instead of g, it's a R harmonic. But nevertheless, R harmonic functions do not attain maximal values So there is no way for them to go to 0 as the absolute value of x goes to infinity. So this is sort of a very nice argument that we try to sort of, it would be very nice to have something related that could deal with ratio limit boundaries, but so far it doesn't work. And it would also be very nice to have like, I don't know, a map like this that would be able to treat things, to have an argument like this that would be able to treat things other than relatively hyperbolic groups. So yeah, so these are some questions. Okay, and I'll finish off now.
Right, yeah, thank you very much. Yeah, let's thank Ilya. Yeah, thanks.